Okay, gentlemen. So what I'm going to do today is I'm going to go through your worksheet and just write out all the answers and talk about why they are what they are. So this should be a relatively short video. Ideally, you would have done some of this on your own. I understand that you can use this to just blatantly copy, but you won't learn anything. And again, there will be a quiz this Friday on this. So you should probably try to learn some of this stuff. So starting with the first three, letters A, B, and C, they're all labeled combustion. And all of them, the thing being reacted with oxygen. So it's this oxygen that makes the combustion. But what's being reacted with oxygen is a hydrocarbon, something made out of only hydrogen and carbon and optionally oxygen. And whenever you have a combustion of a hydrocarbon, no matter what that hydrocarbon is, combustion of a hydrocarbon always gives you the following products: CO2 plus H2O. Always. For all of these, the products are going to be the exact same thing. Now, they would balance differently, and if you want to practice balancing, you can balance them, but they're all going to give you carbon dioxide and water. You do not have to balance these equations. I did not ask you to do that, so if you did, good for you, but you are not being asked to do that. So moving down to number one. Number one is a synthesis. It tells us that. Magnesium plus iodine. Well, they're going to combine because it's synthesis, so that's what happens. And you'll get magnesium and iodine together. However, whenever you're making an ionic compound, something made of a metal and a non-metal, you have to check the charges. Magnesium is +2 because of where it is on the periodic table. Iodine is -1, also because of where it is on the periodic table. So to cancel out that magnesium, to cancel out that +2, you need 2 iodines. So it's going to make MgI2. Again, it's not complicated, just as long as you do all the steps. The next one's a double displacement, and it is copper 2 chloride and hydrogen sulfide. So it's a double displacement. The copper is going to change places with the hydrogen. Copper has a positive charge and hydrogen has a positive charge. So you're going to end up with copper. It's going to go with the sulfur. And the hydrogen is going to go with the chlorine. And now, again, we have to check the charges. Now, copper, you don't know its charge. Copper is in that middle group of the periodic table where you don't necessarily know its charge. However, and this is important, charges won't change from one side of the equation to another, at least not as we're doing it. So we're going to check everything else's charge. Chlorine is always -1. Hydrogen is always +1. Sulfur is always -2. I get all of those from their spots on the periodic table. If I bring up periodic table here, come on, you can do it. Oh, that's a mirrored one. So if I bring up a periodic table, you can see that hydrogen is over here. That whole column is +1. The magnesium, by the way, was over here. That's why it's +2. So we had hydrogen, which is +1. Copper, which is over here, 29, is in the middle. That's in the D block. We don't know what that is without some other clues. Chlorine is always -1, and sulfur will be -2. Remember, nitrogen down -3, oxygen down -2, fluorine down -1. So we've got our copper chloride and our hydrogen sulfide. As you can see, hydrogen, there's 2 hydrogen +1s to balance out the -2 on the sulfide. You can make the same assumption about the first thing here. So we have 2 -1s, which means the negative side, the chlorine side, is total of -2. So copper must be, to balance it out, it has to be +2. So we can bring that over to this side. Copper +2, sulfur -2, +1 for hydrogen, and -1 for chlorine. Those cancel out. The +2 and -2, copper 2 sulfide, that cancels out and is fine. And hydrochloric acid, H is +1, Cl is -1, that cancels out too. Again, you could balance it, but you don't have to. So for that, all you have to do is what I have here, copper 2 sulfide plus hydrochloric acid. ZnCO3 plus heat. So whenever you only have one chemical, it's going to decompose. This is one that I figured you could either look up. It's a little more complicated. It doesn't go all the way down to zinc, carbon, and oxygen separate. What actually ends up happening is you end up with ZnO plus CO2. And again, if I give you a decomposition on a quiz or something, it'll just be made of two things, like H2O or MgO, and all it'll do is split into its separate parts. But here you see decomposition that can split into, you know, smaller parts, but not all the way down to its individual element. Going on with single replacement with hydrochloric acid and zinc. For this, you would have to check that zinc can replace hydrogen on the activity series. So anytime you have a single replacement reaction, something where it's a metal or non-metal by itself, an element by itself, with either an ionic compound or an acid, in this case we have an acid, what you're going to do is you're going to check on the activity series. These are the activity series. Remember, for single replacement reactions, things above can replace things below. So we have zinc here trying to replace hydrogen. Zinc is higher than hydrogen, so it can replace it. So this reaction will go forward, back to here, and you'll end up with here, zinc with chlorine plus hydrogen by itself. Couple things. Zinc is always +2. That was one you just had to know. So +2, chlorine is -1. So it's ZnCl2 because you need two negative ones to balance out a +2. Another thing is that hydrogen is one of those Brinkelhoff diatomic molecules. It's the H in Hoff and Brinkelhoff, so it's never H by itself. It's always H2. So the proper way to do this is ZnCl2 plus H2. So next one, Na plus MgCl2. We got an element by itself plus an ionic compound. That's going to be a single replacement reaction. And once again, we have to check to see if magnesium is higher up, or sodium, excuse me, is higher up than magnesium. Because sodium wants to try to replace that magnesium. They both want to be with the chlorine. Only one of them is going to get to. So we check on the periodic table. As we see, sodium is above magnesium. Sodium's right here, magnesium's right here. Oops, wrong thing. So sodium can replace magnesium, and so it will. So the sodium will end up with the chlorine, and then the magnesium will be by itself and sad. And again, you check the charges. Sodium, because of where it is on the periodic table, is +1. Chlorine is -1. They cancel out, and you're done. And since this is a single replacement, you should also, and I'm just going to write SR here, and that's fine if you do that too. You should label that, since this is the first one that isn't labeled. Next one, number 7. 2 ionic compounds. So you have 2 ionic compounds. In other words, a metal plus a nonmetal, and another metal plus a nonmetal. That is a sure sign of double replacement reactions, where the positive parts, the calcium and the potassium, in this case the metals, are going to switch places. So you're going to have a double replacement reaction, and the metals are going to switch partners. So what you end up with is calcium with this carbonate, CO3, that's on your polyatomic ion sheet, and you end up with, potassium with chlorine. And again, just like before, K looks terrible, let me just get rid of that. Just like before, you have to check the charges on everything. Well, calcium's +2, carbonate is -2. You'd look that up on a polyatomic ion sheet. Potassium's +1, chlorine is -1. So both the calcium carbonate with its +2 and -2, and the potassium chloride with its +1 and -1, those are all set. They don't need to be balanced in any way. And we aren't balancing the whole equation. The only thing you have to balance here is the products, the ionic compounds. So you're good there. Next one, we have two elements by themselves, potassium and chlorine. Now, chlorine's a Breakelhoff, so even when it's by itself, it's Cl2. But two elements by itself, all they can do chemically is combine. So this will be combination or synthesis, if you prefer calling it that. So combination or synthesis, they will combine into KCl. And again, you check the charges. Potassium is +1, chlorine is -1, just as over here. It's just KCl. That's it. Because we're not balancing the whole equation, you have to worry about the fact that there's two chlorines here and only one over here. But if you wanted to go and balance it, you could. Okay, number 9. Barium chloride and potassium phosphate. So, two ionic compounds, metal and a nonmetal, or a metal and a polyatomic ion. Again, we're looking at a double replacement reaction where barium and potassium, the positive parts, are going to try to switch partners. They are going to switch partners. So you're going to end up with, let's see here, potassium, the K, going with the chlorine. We've seen a whole bunch already how that's +1 and -1. And then you'll end up with the barium going with the phosphate. Now, phosphate is a polyatomic ion with a -3 charge. Barium has a +2 charge. So the only way for these to balance out is for both of them to go to 6. In other words, you need enough bariums to be +6 and enough phosphates to be -6. So barium +2, you would need 3 of them to be +6. Since we need more than one phosphate, we have to put the whole thing in parentheses, and we need 2 of them to be -6. So 3 + 2s, 3 bariums, gives us +6. 2 -3s, 2 phosphates, gives us -6, and those cancel out. So you get KCl plus Ba3 PO4 in parentheses 2. That's another double replacement. The next one, aluminum carbonate plus heat. And again, here's another one. It's just one thing plus heat. There's only one chemical. So this is going to be decomposition. It's going to break up. And if you broke this all the way up into aluminum, carbon, and oxygen, that'd be fine. I don't expect you to know decomposition routes, and I'm only going to give you, again, really simple ones with 2 elements. What this actually breaks into is aluminum oxide, which is Al2O3, plus CO2, carbon dioxide. It turns out whenever you can break off a CO2, generally that's something that breaks off first. So that's how it goes. Next one, aluminum and oxygen. Aluminum and oxygen is going to be a combination or a synthesis. I'll call it a synthesis this time. I don't care which one you prefer to call it. So you have a synthesis with aluminum combining with oxygen. It's going to be a metal and a nonmetal, so you have to balance the charges. And just as the previous one, it'll be Al2O3. The reason for that, aluminum is +3, oxygen is -2. So again, you're going to +6 and -6 in order to balance it. So that 3-to-2 ratio. Final one in this section is lead-2 nitrate and potassium hydroxide. This one's difficult. It's going to be a double replacement where the lead and the potassium try to replace one another, switch partners, and they do. So you get potassium with nitrate and lead with hydroxide. So a couple things about this. Again, we're going to have to look at the charges. Nitrate, polyatomic ion, always -1. Hydroxide, the OH minus is also -1, and potassium is +1. So potassium is going to stay +1, nitrate's going to stay -1, and hydroxide is going to be -1. But that lead is in the middle of the periodic table, or at least in part of the periodic table. It's one of the ones that gets a Roman numeral. Lead can be either +2 or +4. And you don't have to know that. You'll be given a Roman numeral. But in this case, you can actually figure it out. Since you have, in lead nitrate, two nitrates, two negative ones. That means the lead must be plus 2. It has to be, otherwise that would be an incorrect formula, and I won't give you incorrect formula. So if lead is plus 2 and the hydroxide is minus 1, that means lead 2 hydroxide looks like that. I should put a plus in between. So I end up with potassium nitrate, KNO3, and lead 2 hydroxide. So that is that first section of your worksheet. The next section, we're just identifying and balancing. So we aren't worried about predicting products in this case. We're just identifying. The first one, clearly, we have two ionic compounds, sodium with bromide, calcium with hydroxide. And we see that the positive parts, the calcium and the sodium, switch partners. That's a double replacement reaction. And to balance it, well, we have one sodium on each side, one calcium on each side. But we need two bromines, so I'm going to go with bromines. Two bromines over here, so here's what I'm going to do. I'll actually go through Na, Br, Ca, and I'm going to do hydroxide as one thing. Move it over here a little bit so we can see. Na, Br, Ca, OH. So I'm treating the hydroxide as one thing, and you can do that with any polyatomic ion, assuming it's the same on both sides. So starting off, 1, 1, 1, 2. Over here we have 1, 2. Let's see, 1 calcium and 1 hydroxide. So really quickly, bromine, I need 2 bromines over here, so I'll put a 2 here, 2 sodiums, and 2 bromines. So go back and look at sodium, I'll put a 2 here, 2 sodiums, 2 hydroxides, and I'm balanced. And that's it. It's entirely balanced with 2 sodiums, 2 bromines, 1 calcium, and 1 hydroxide on each side. So that's the first one. Second one, which is number 3, because, you know, I took these out of order. I didn't give you all the problems. The second one is going to be, well, pretty easy to recognize. Anything plus O2 is combustion. If it's an element by itself plus O2, it could also be combination or synthesis. Either reaction, either answer would be fine. But in this case, it happens to be combustion of a hydrocarbon, which means you're always going to get CO2 plus H2O, and we're going to balance it. Carbon, hydrogen, oxygen, carbon, hydrogen, oxygen on each side. 1, 2, 3, 5, 9, 3. Again, I'll do carbon first, hydrogen second, and oxygen third. So looking at carbon, first I will put a 5 here, which allows you to have 5 carbons, and then 10 oxygens plus 1 is 11. Looking at hydrogens, I have 9 over here, and I need to get to 9 on this side, but I can't do that. I can't get from 9 to 9 on this side because H2 is, no matter what I do, I'd have an even number. So I'm going to have to go back, double this, so that means I will have 10, 18, 2 plus 2 is 4. And I'm also going to look back and change this to 10. So that I have 10, 21 oxygens. And now I can do my hydrogens. So I will look at my hydrogens. I'll put a 9 here. 9 will give me 18 on this side. And 9 oxygens plus 20 is 29. So, once again, I find myself with an odd-even problem. I have 2 oxygens here, and I can only increase by 2s. I need to get to 29. So I have to double everything else. And I'm sorry, this is getting kind of hard to read. I'll write it out over here afterwards. But I'm going to double this to 4, double this to 20, double this to 18, and that'll give me 20, 36, 36, 20. and 48, I believe. 29 times 2 is, no, that's not right at all. It's 58. I can do math sometimes, I swear. So 58 oxygens on this side, which means I have 4 from the, and you have to be careful here, I have 4 from the hydrocarbon here. And so I need 54 additional ones. So to get to 54 additional ones, that would be 27, and that gets me to 58 total. So again, I'm going to rewrite this. It's going to be 4 C5H9, excuse me, C5H9O plus 27 O2s, and that is going to give you 20 CO2s plus, and I'm going to go down, plus 18 H2Os. So that's the final balanced one for there. Sorry, that got a little messy. You had to do the doubling trick twice. But you do, in fact, end up with the same number of carbon, 20, hydrogen's 36, and oxygen's 58 on each side. It does work. It's just kind of a pain. But you get there. So last one is going to be, or at least it's going to be a single replacement reaction. We don't have to check it out because I've already given you the product. So it's a single replacement reaction where lead is, in fact, higher than hydrogen. So here's lead, here's hydrogen. Lead can replace hydrogen, and it will. So we are just going to balance everything. And again, I'm going to treat the phosphate, the ionic compound, or the polyatomic ion as one thing. So we have Pb. Oops. So we'll have lead, hydrogen, and PO4 on each side. And I'll count them up initially. 1, 3, 1, 3, 2, 2. So I'm actually going to start with hydrogens because lead's by itself, and in this case that makes it easier. It doesn't matter if you start with lead. I'm just going to start with hydrogen because I already know I'm going to have to do this. So I'm going to do this to get 2, and, or to get, excuse me, not 2, 6. 6 of these and 2 of these. The reason I knew I'd had to do that is because I have H2 over here, and it's even. So if I only had 3, there'd be no way to do that. 3 here, get a 6. And now all I have to do is sort my leads. And as you can see, lead is by itself. So I can put a 3 there, get 3. I have 3 leads, 6 hydrogens, and 2 hydroxides on each side. If you want, you can put the 1 here, or you can leave it blank. And this is a single replacement reaction. Okay, for this last part, I'm not going to go through individually and work through all the problems. I have the answers up here. I will also put the answer key as like a PDF or something online. But the first one, I'm just going to go over some highlights. Magnesium carbonate is heated strongly to produce magnesium oxide and carbon dioxide gas. Again, with the magnesium carbonate and the magnesium oxide, metal plus a non-metal, metal plus a polyatomic ion, make sure you check the charges. And it says carbon dioxide gas, so I did put that little gas there, little G, in parenthetical subscript for carbon dioxide. Hydrogen peroxide, I figured you could look it up. Hopefully some of you actually did, which is H2O2 decomposes to produce water and oxygen gas. So it's H2O2, it decomposes, so just an arrow, and it produces H2O and O2. Again, it says gas, so I put the little G there. Zinc metal is added to a solution of iron 2 sulfate. So zinc has a charge of +2. It's one of those that you just have to know. Zinc, cadmium, and silver are the ones in the D block. Zinc that you just have to know. Zinc and cadmium always have +2. Silver always has +1. So when the zinc combines, excuse me, with the sulfate. It kicks the iron off. This is a single replacement reaction. Zinc is higher than iron on the activity series, so zinc can and will remove iron from the sulfate. So zinc gets to go with the sulfate. Zinc is +2, sulfate -2. So you don't have to do anything with that. And then iron by itself, you don't have to worry about the charge. When a metal's by itself, it doesn't have a charge. It is just neutral. There's one of everything in this one: zinc, iron, and sulfate, if you take sulfate as a whole. So you don't have to do anything as far as balancing. It's all just ones. The last two are both combustions of hydrocarbon. It says ignited in air, but whenever you have a hydrocarbon and it's ignited, that means it's reacting with the oxygen part of air. So I did put that there. Make sure you understand that. And then the balancing, as you go through, you can do the balancing on your own. You can see my final answers here and kind of the path I took. A couple, I mean, the combustions can get to kind of high numbers, so they're a little difficult, but overall it's just balancing. So that's the worksheet. Again, if you have any questions, be sure to ask me in a Zoom meeting, or if you need to in an email. Zoom meeting would probably be better. And remember, we have a quiz Friday on this stuff. So this is what the quiz will be like. It'll be predicting products, balancing equations, and identifying reaction types. That's what will be on the quiz. So hopefully you are prepared for that. That is all for today. Again, I will put this key up in either PDF or some form on PowerSchool and the Google Classroom page as well.